Chapter 11, Section 4, Key Properties of Eigenvalues and Eigenvectors. As we saw in the previous section, eigenvalues and eigenvectors have these key properties. We saw these three properties in the previous section. This section will cover these three properties: orthogonality of eigenvectors in symmetric matrices, inverse and eigenvalues, and eigenvectors and matrix powers. The next property is orthogonality of eigenvectors in symmetric matrices. If a matrix A is symmetric, all its eigenvalues are real, and its eigenvectors corresponding to distinct eigenvalues are orthogonal. This property is crucial in applications such as principal component analysis and many optimization problems. Let's confirm this using a simple example. Consider this symmetric matrix A. As the first step, find the eigenvalues. Using the determination, we can obtain the eigenvalues. They are 5 and 2. As the second step, find eigenvectors for each eigenvalue. As we already know, we can find eigenvectors in this way. Now we obtain two eigenvectors, v1 and v2. Next, let's verify the orthogonality. Compute the dot product of these eigenvectors. We can find that it is 0. It indicates that the eigenvectors are orthogonal. Let's prove the property that eigenvalues of a symmetric matrix are real. Let A be an n by n symmetric matrix. Suppose lambda is an eigenvalue of A, and let V be a corresponding eigenvector. Take the conjugate transpose of both sides. Using the property of transposes, we can obtain this equation. Since A is symmetric, we substitute A transpose with A. Next, multiply both sides by V. Let's continue with this equation. Since the inner product of V transpose and V is a scalar, it is real and positive if V is not equal to 0. Therefore, lambda can be expressed in this way. Both the denominator and numerator are real, lambda must be real. So, all eigenvalues of a symmetric matrix are real. Let's go on to another side. Eigenvectors of distinct eigenvalues are orthogonal. Let A be symmetric, and suppose v1 as v2 are eigenvectors corresponding to distinct eigenvalues lambda 1 and lambda 2. Consider this inner product, and take the transpose of A v1 equals lambda 1 v1 and multiplying them by v2. Using the property of transpose, we can rewrite this equation in this way. Since A is symmetric, this equation holds. Thus, this equation holds. Let's continue with this equation. Rearrange this equation. Here, lambda 1 is not equal to lambda 2, so this equation must hold. This shows that eigenvectors corresponding to distinct eigenvalues of a symmetric matrix are orthogonal. The next property is about inverse and eigenvalues. If a matrix A is an invertible matrix with eigenvalues lambda 1, lambda 2, lambda n, the eigenvalues of the inverse of A are these fractions. Besides, the eigenvectors of A and A inverse are the same. Let's confirm this using a simple example. Consider this symmetric matrix A. As the first step, find the eigenvalues of A. This can be done using this characteristic equation. Let's continue solving the characteristic equation of A. Using the quadratic formula, we can find the two eigenvalues of A. As the next step, find the eigenvalues of A inverse. They are simply the reciprocals of those of A. Let me show the mathematical proof of this property. For a matrix A with eigenvalue lambda and corresponding eigenvector v, we have this equation. In this case, A is invertible, so we can multiply both sides by A inverse. Let's simplify the left side. Next, divide both sides by lambda, assuming that lambda is not equal to 0, since A is invertible and thus has non-zero eigenvalues. We can see that the first point of this property is met, and the eigenvector of A inverse is the same as that of matrix A. The final property covered in this section is about eigenvectors and the matrix powers. If V is an eigenvector of a matrix A with eigenvalue lambda, the eigenvector V is also an eigenvector of k to the power of k, and its eigenvalue is lambda to the power of k. Let's confirm this using a simple example. Consider this matrix A. The eigenvalues of A are lambda 1 equals 2 and lambda 2 equals 3, with the following corresponding eigenvectors. Next, compute the square of A. Let's continue with the square of A. The eigenvalue of V1 for the square of A can be obtained in this way. It is 4. For V1, we can obtain the eigenvalue in similar way. It is 9. Let me show the mathematical proof of this property. Let me start with this equation. Using induction, let me show that V is also an eigenvector of A to the power of k with eigenvalue lambda to the power of k. As a base case, we start with k equals 1, which is just the definition of an eigenvector. So, V is an eigenvector of A1 with eigenvalue lambda. Next, assume that for some k, the following holds. We need to prove that it holds for k plus 1. For matrix exponentiation, we know that a to the power of k plus 1 equals the product of a and a to the power of k. Applying this to the eigenvector v. Using the induction hypothesis, the following equation holds. Since lambda is a scalar, we can factor it out. Using the definition of an eigenvector again, we can rewrite the equation in this way. This equation proves that V is still an eigenvector of A to the power of k plus 1 with eigenvalue lambda to the power of k. Now we have shown that for all k, the following equation holds. This means that V remains an eigenvector for all powers of k. And the corresponding eigenvalue for A to the power of k is lambda to the power of k. Thank you for watching. Please thumbs up and subscribe to my channel.